Hi, this is Professor Fernandez. We're working on class note C in lesson 6. So in this class notes, we want to find the general solution of this non-homogeneous solid. And the right-hand side here, e to the t, is kind of complicated in terms of what we did in the previous video to find the particular solution, where I introduced you to this very fancy method that I called method of staring. So we're not going to do that here because, as I said, this right-hand side is too complicated. Let me just illustrate. If you tried, to solve this using method of staring, you would say, well, what if I pick some functions for y of t that are simple enough? Maybe they solve the ODE. If I pick a constant function, the second derivative is 0, and this would just be minus k equals e to the t. That's not going to work because the exponential is not a constant function. So you might think, oh, well, what about e to the t, right? Maybe pick something that involves the right-hand side. So that's a good guess. The second derivative of e to the t is e to the t, and then minus e to the t, that gives me 0. It does not give me e to the t. So, method of staring, we tried it, but it didn't work. So we need something more sophisticated. And that's the point of this example, really, to go up to the previous page and to talk about the variation parameters approach. So this is theorem 6.3.1 up here. So what does this say? Variation of parameters. Suppose y1 and y2 are two solutions to the homogeneous solid with p of t and q of t continuates. That's our usual setup. And let G be continuous on the interval alpha to beta. And y1 and y2 are notations for the fundamental solution, so we'll clarify that. Then a particular solution to the associated non-homogeneous solid on this interval is, so let's take a look at the structure of this. We have a linear combination of y1 and y2, but instead of the linear combination involving constants, it involves these two new functions u1 and u2. And how do we find these new functions? Well, this is the essentially nuts and bolts of the method. So the derivative of u1 is given by this quantity. The derivative of u2 is given by this quantity. So that's something that we have to set up and integrate to find u1, u2. And then once we do that, we just substitute it back into this definition for the particular solution, this form for psi. Okay, one thing to notice about the derivatives of u1 and u2, these formulas, they involve g of t. Okay, so that's somewhat to be expected. This is a method for solving the non-homogeneous solid. And the denominator is the Wronskian. So the Wronskian makes a comeback, right? And again, y1 and y2 are assumed to be fundamental solutions, so we know that the Wronskian is non-zero. So that's one of the reasons that, how all this connects. Okay, so what I'm going to do is now apply the variation of parameters approach to solve the ODE in this example. You can see that I've typed out already a lot of the steps so that I can save some time in this video and focus on the concepts. So step number 1, solve the homogeneous ODE. That's exactly what we did in the previous video. And that comes again from the theorem that tells us the general solution to a non-homogeneous ODE is the sum of the solution to the homogeneous version of the ODE plus psi, the particular solution. All right, so for the homogeneous ODE, what would it look like? Well, it would be replace this with 0. So we're looking at y double prime minus y equals 0. So there we go. This is a CC solid constant coefficient, second order linear ODE. Its characteristic equation is r squared minus 1 equals 0, which factors into r minus 1, r plus 1. And therefore, it gives you the two solutions, -1 and 1. So the r equals 1 solution gives rise to this y1 e to the t solution to the ODE. The r equals -1 gives rise to this y2 e to the minus t solution. And we can check that those solutions are fundamental solutions, meaning that their Wronskian is non-zero. Great, so we have found the first two ingredients in the variation of parameters formula approach, which is to find the fundamental solutions to the homogeneous version of the original non-homogeneous ODE. Great, so second step. So now let's go ahead and find the particular solution. So we're going to use the variation of parameters theorem. To do that, we're going to calculate the Wronskian of y1 and y2 because, again, that's in the denominator of those u1, u2 derivative formulas. So Wronskian, remember this is y1 times y2 prime minus y1 prime times y2. All right, and y1 is e to the t, so that's there, and y2 is e to the minus t. That's its derivative. You bring down a -1 because of the chain rule. And then minus y1 prime, e to the t's derivative is e to the t times y2. Great, so if I remove the clutter here, so we can do some of the simplification. This is negative e to the t minus t minus e to the t minus t. So that's negative e to the 0 minus e to the 0, -1 minus 1, -2. So that's where that comes from. Great, so we get our Wronskian, and that's again going to be the denominator of the u1, u2 prime formulas. All right, so then now let's go ahead and find those, right? So here is the u1 prime formula, here's the u2 prime formula, and now we just substitute everything we know. One quick thing to know, right, to notice is that up here, I'm going to need the g of t, all right? Now let me scroll up really quickly to point something out that is very easy to notice. This is a common mistake when applying variation parameters. This is the ODE form from which variation of parameters, the approach was developed. What I want you to notice about this form of the ODE is that it is in the standard form. Right? That means a lot of things. In particular, it means that the coefficient of y double prime is 1. Right? You can't see it, so that's a 1 there. If the ODE that we were working on was something like 5y double prime minus y equals e to the t, then g of t would not be e to the t. All right? So not for the purposes of variation of parameters, because the whole theorem assumes that this is the form of the ODE. Right, so we would have to go in here and divide by 5 to obtain this ODE, e to the t over 5. And then this would be my g of t, all right, for the purposes, again, of this theorem. All right, so that's important because it's very easy to forget that and write down a g of t function that is ever so slightly different from the actual g of t that's assumed in the variation of parameters formula down here. And then, you'll check your solutions or something, and it will be slightly different from what it should be. And you'll spend hours and hours figuring out why. Turns out you just forgot to divide by 5 or something like that. Okay, so back to this example. For u1, right? Notice that g of t equals t. There we go. I'm kind of reminding you, but verbally also I added this little tip that, again, you want to make sure the ODE is in standard form. And the Wronskian down here, we just calculated it, is -2 up here. So that goes in the denominator right here. And then g of t, because, again, the coefficient of y double prime is 1, is legitimately e to the t. So that is g of t. I have a minus sign in front, because I'm doing the u1 prime formula. And then y2, remember y2 is e to the minus t. Okay, great. So I have this product of e to the t and e to the minus t. That's e to the 0, that's 1. So I get 1 on top, and then negative divided by -2, that's 2. So I get u1 prime is 1/2. Now when I integrate both sides, right, I'm solving for u1 because I know its derivative. I integrate both sides, I get 1/2 t. Now you might say, Professor, it's 1/2 t plus c, right? Remembering your calculus professors constantly bothering you about, not forgetting the plus c's when you integrate indefinitely. And I totally agree. However, it so turns out, this is probably the one time in your life when you'll hear a math professor say, you can forget the plus c. So I'm explaining here why that is, right? If we leave out the arbitrary constant, if we include the arbitrary constant, then we end up duplicating the general solution to the homogeneous version of the solved. So I say more about that in the end of this lesson notes, right after the practice problems. Long story short, because psi is u1 y1 plus u2 y2, if this y1, if the u1 that we find, here it is, ends up having, whatever it is, plus the c that would pop out of the integration, then, let's say c2, c1, then you can see that when I multiply this out, I'm going to get u1 y1 plus u2 y2. That's the psi I would have gotten if I did not include the plus c. And then plus c1 y1 plus c2 y2. This is the general solution to the homogeneous problem. This is the psi I would have gotten if I didn't include the plus c. So by including the plus c, when I actually write out psi itself, I'm just getting the general solution to the non-homogeneous ODE, the sum of the solution to the homogeneous plus the psi without the plus c. Okay, so that's a very quick tour, brief explanation of what I wrote in that supplementary content section. So again, I'm going to, in solving for u1 and u2, by integrating, I am not going to add here the plus c. All right. Okay, so we have found u1. Now for u2, it was a very similar expression. So it was g of t times y1 divided by the Wronskian. So that's up here, g of t, y1 divided by the Wronskian. Okay, so g of t in this problem, again, is e to the t, so that explains that. Y1 is also e to the t, and the Wronskian is -2. So I get minus 1/2 e to the 2t. Great. And then I integrate that, so I'm going to integrate this e to the 2t integrates to 1/2 e to the 2t. That's a little u substitution that we have to use. So then that's where we get a 1/2 times the original 1/2 that was there, gives us a 1/4. And then we carry over the -1 to give us -1/4, and then e to the 2t. So I found my u1 and my u2, and then I go back to the form for psi that's dictated in the theorem. So it's u1, which was 1/2 e to the t, times y1, which was, oh, sorry, it's the other way around. U1 was not 1/2 e to the t. U1 was 1/2 times t, right? So that's u1 times y1, which was e to the t. There we go. And then the rest of it, we just continue with the products. U2 times y2 gives us that. And then simplifying all this, this is e to the 2t times e to the minus t, which is e to the 2t minus t, which is e to the t. Okay, so this second term here is minus 1/4 e to the t. So these two terms have an e to the t in them. They also have a 2 in the denominator. So we factor that out, and then we get this expression on the right-hand side. So that is my psi from variation parameters. Finally, Theorem 6.2.1, I'll remind you what that is in a minute, tells us that the general solution is the sum of the solution to the homogeneous problem, which is c1 y1 plus c2 y2, plus psi. All right, and then I'll just scroll up really quickly to remind you what that theorem says, which effectively is what I just said, but just so you see it, there it is, right? So the general solution to the non-homogeneous soled, again, there are assumptions that we need to check, like y1, y2 being particular fundamental solutions. The general solution to the non-homogeneous soled is c1 y1 plus c2 y2, the usual solution when y1 and y2 are homogeneous, are fundamental solutions to the homogeneous soled, plus psi. All right, so scroll back down so we can finish up and wrap up this problem. So that's the end of this problem. So general takeaway, right? I'll just scroll up really quick. We've now done 2 examples. This is the second, and the previous video was the first, of solving non-homogeneous solds. And the 2 methods that you have now learned for finding the particular solution are the method of staring, which again, is I copyrighted this method. I'm kidding. But this is not a sophisticated method. This is a method, however, that you should not ignore, because like we saw in the previous problem, it may yield some quick particular solutions. If this doesn't work, then that's where you can try variation of parameters. This is a more systematic algorithmic method, but as you can see on this page, it does take a lot longer. So, all this work to find psi. And that's because, the integrals that we obtained for U1 and U2, the integration process, was fairly simple. But again, if the GFT and other functions that are involved here are complicated, you might be integrating to solve for U1, U2, and you might be doing that for a while. So you definitely want to avoid variation parameters if at all possible, which was the intent of talking about at least one other method to find psi.